Hi everyone. So in this video, we're going to look at a specific example of how we can use the 3D models to help us visualize the shell method. So we're going to be looking at a solid of revolution and setting up an integral to find the volume. This is the same exact solid that we used with the washer method, but we'll see that we can also find the volume using the shell method, and once we have that set up, we can compare both of them and see which method ended up being the simpler one. So we're taking this parabolic region, so the region bounded by y is equal to negative x minus 3 squared plus 4, and y is equal to 0. So that would be this region here. And we're revolving it around the y-axis. And so from the side, we would see something like this. Oops. But it's actually a three-dimensional shape, and we'll look at that in a moment with the actual model. But one thing I just want to mention is just to kind of get you thinking about what's the difference between the shell method and the washer method. So with the washer method, and this is the same idea behind the disk method, you're taking your solid and you're kind of just slicing it. So picture kind of taking this three-dimensional shape and slicing through it in this direction. And so if you do that all over, right, take all these different slices, we saw in our last video, the one about the washer method, we saw that all those slices are going to be these kind of donut shapes. And so if you can add up the volumes of all of those different slices, that would give you the total volume of the solid. And so the shell method in some ways is very similar, and in some ways is quite different. So what is similar about the shell method? Well, we're still taking our solid and breaking it into these smaller pieces and using an integral to add up all the smaller pieces to find the total volume. But the way we're breaking the shape up is very, very different. Instead of slicing the shape, we're kind of finding these nesting cylindrical shells. And so I want to now look at the 3D model so we can kind of visualize what's going on with these nesting cylinders. So this is the solid that we're going to be working with in this video. I'd recommend taking it out so you can actually kind of look at it yourself. We mentioned this last time that this solid, the one that we did with the washer method in that last video, they're the same, right? It's the same solid. It's just kind of a different approach to breaking that solid down. So again, with the washer method, the idea is that if you take out this plastic piece, this is the shape we were revolving to find the solid. And then we're just slicing it, like I said, this way, right? Slicing it this way. And what do the slices look like? They look like this. The shell method, on the other hand, so let me take out, again, this little plastic piece that represents the shape we're revolving. So again, we have this parabolic shape. And then the way that the shell method works is we're kind of, if you look at this shape from the top down and you picture all of these kind of concentric circles and each of them going down all the way to the solid, you would have these different cylinders, right? So this one is a little trickier to take apart. I have to kind of pull out the inside. But we can see that the shape would break down into these cylindrical shapes, right? So the inside of the shape is missing, but I'm just going to put this back in for a moment. You can kind of imagine, right, if you had more and more of these things in purple kind of extending outward on the shape, you would be able to build up the whole shape out of these little cylinders. So again, we're not slicing it across, we're kind of going the other way, where we're going, thinking of it kind of inside out, being made up of all of these different cylinders. And so the idea behind the shell method is that rather than adding up those cross-sectional disks or washers, instead what we're going to add up is the volumes of each of these cylinders. And so how do you find the volume of a cylinder like this? Well, basically, it can be rolled out into a rectangle, right? And instead you can think of it as this kind of rectangular solid where you would do base times height. So the base is the same as the circumference of this cylinder, right? And how do you find circumference? Well, circumference is 2 pi times the radius. And so this length, the long length would be 2 pi times the radius, right? And then the height, well, that is going to come from the height of the function. And we'll get into that when we go back to our example. And then you would multiply also by the thickness. And so we'll see how that plays out in the shell method formula for finding the volume. But, I think it's just really hard for some people to visualize what's going on with the shell method. So I hope that this helps. And again, like, I want you to think about not just this one purple piece, but imagine that this whole shape was made up of those. Like, look at it and try to imagine what would it look like if instead of just having this one purple piece, you had all of these different cylinders kind of one within the other. And so, this one somewhere in the middle, you would have more of them on the outside. And then this piece that came from the inside, this would also be made up of those cylinders. Okay, so let's get back to the example and actually set up this integral. Okay, so as we mentioned, the way that you find the volume using the shell method is instead of thinking about you're using an integral to add up cross sections, you're now using an integral to add up the volumes of these cylinders. So as we said, the volume of one of those cylinders is going to be 2 times pi times the radius, that comes from the circumference, times the height, and then times either delta x or delta y. Okay, so now that we've had an idea, we've been able to kind of look at what these cylindrical shells look like, let's try to sketch one ourselves within the context of this picture. So the way that I like to sketch them is just to choose some point on your curve, on the original curve. Then, because of symmetry, you can go directly across and kind of just identify the same point on the other side of your solid. And then, because this is going to be a cylinder, you want to connect them with this kind of circular shape, right? Like a 3-dimensional circular shape. And then the height of the cylinder, well, that's going to go all the way down to the bottom of your solid. And in this case, the bottom of the solid is just on the x-axis. And then we can finish it like this, and we see that we have this cylinder. And so we would have all of these different cylinders. Maybe I'll even draw a couple more just to kind of give an idea. So like for another example, maybe we could draw one here. So choosing the same height on both of them, going across, going down to the very base of our solid, and then finishing it off like this. You would have more of them out here. So for example, if I could go here and do the symmetric point over here. This is going to be like a really big one. But it's shorter, right? This one would be shorter than the purple one that I drew first, but it would have a much bigger radius. And it would look something like this. So you're gonna have all of these different cylinders all kind of fitting together to give you the whole solid. But I'm actually gonna now erase some of these because I think it will make the picture more cluttered as we're trying to set up our integral. So let me just get rid of this and this. Okay, so focusing now on this, this original one we drew, there's one piece that's kind of missing from this, which is it's supposed to have kind of a thickness to it, right? Because we're going to be adding up volumes, not areas. And so I'm just going to add within this cylindrical shell this kind of idea of thickness here. So we're imagining that it does have a little bit of a thickness to it. And so one thing that we're going to need to figure out when we're setting up this integral is which variable are we integrating with respect to. And just like with the disc and washer method, you want to think about whether the thickness, because the thickness of your discs or washers or shells, that's where the dx or dy is going to come from. And so you want to think about whether that is a horizontal or a vertical measurement. And in this case, it's horizontal, right? If you were to measure this thickness, that would be delta x. It would be a change in x. And so that tells us that when we set up our integral, we're going to be integrating with respect to x rather than with respect to y. So our integral, or our volume formula, is basically going to be an integral from a to b, and we'll talk about where those bounds come from when we get to setting up the specific one, of 2 pi times the radius. So that, again, when we took that cylinder and kind of stretched it out into a rectangle, that was like the base of the rectangle, and that comes from the circumference of the cylinder. And then we have to multiply times the height, and we'll see that the height is going to come from basically the function. And then we also have dx, and dx rather than dy, that's because the thickness was measured horizontally. And actually, let me just color code this a little bit here. So maybe I'll use green for the radius and orange for the height. Okay, so now let's figure out what this would be for our specific function. So I'm going to leave the bounds blank for now, and I'm also going to pull the 2 pi outside of our integral, and we'll come back to those bounds. So what is the radius going to be? Well, the radius is the distance from the y-axis to your curve. And if you think about all of the different cylinders that you can draw, well, they have all sorts of different radii, right? And every time we draw the radius, notice that the radius in this case is exactly the same as the x value to which the radius extends, right? So in this case, what is the radius that I just drew in green? Well, it's 2. And 2 is the same as the x value that our radius kind of ended at. It's the same as the x value where we kind of started to draw this cylinder. And so that means that the radius is just x. And another way to think about that is that the radius can really be anything. You know, we're going to have some bounds to control like the lower and upper bound of what the radius could be. But in between those two values, the radius could be anything, right? We could have a radius of like 1.1, 1.2, 1.3. You know, everything basically between 1 and 5 is going to be a valid radius. And so by just making the radius x, that means that it's truly anything, right? It's just any x value that you can choose to go to, that's going to be the radius of one of your cylinders. And so we're going to put the radius in as x. And then what about the height? Well, the height is this distance here, right? So if the radius is x, so let's say, for example, in this case, the radius is x is equal to 2, what would the height be? You know, how would you find the height in terms of x? So again, here, for example, with the radius being 2, how would you use that number 2 to figure out that orange distance? Well, that's what you would get by plugging that x value into your function, right? Like, for example, if we plug 2, that's the radius we have on this specific example. If you plug 2 into this equation, you would get negative 2 minus 3 squared, so that would be negative 1 plus 4, and that would give you 3, and that's exactly the height we have here. So the height is just going to be determined by the function, by plugging whatever x value you're choosing to draw your cylinder at. You're just plugging that into the function to find the height. And so the height here is going to be our function. So negative x minus 3 squared plus 4 dx. Okay, so now what are the bounds going to be? Well, first thing to check, and this is, I think this will dispel a lot of confusion students have with the bounds, is make sure that your bounds match with the variable you're integrating with respect to. That's like the most common mistake I'll see is students will just choose bounds that don't match. Like in this case, if you were to say, for example, 0 to 4, that would not be correct because those are y values and we're integrating with respect to x. It just doesn't make sense. And so really, if we think about it, since x just represents the radius, we just want to think about what is the smallest and largest radius? What is the smallest and largest x value that makes sense to plug into this formula? And that's going to be the same thing as the smallest and largest radius, right? Because whatever the smallest and largest x value could be radii, for both of those, you would just plug them into the height, and that would give you the height of the cylinder. And so you just want to look at what are those smallest and largest radii that could be used here. And so in this case, the smallest possible radius would be 1, right? That's like the first x value that would make sense for a cylinder. It wouldn't make sense, right, to have a cylinder with a radius of like 1/2 or something, because that's not part of the solid. There's a hole in the middle. This cylinder doesn't exist. There's no cylinder in here. And so our first one is 1, and then our last one is 5. And so the bounds are from 1 to 5. And then if you wanted to, you could clean this up a little bit. So you could rewrite this as 2 pi times the integral from 1 to 5 of, if you multiply this x in, you could say like negative x times x minus 3 squared plus 4x. And then if you wanted to actually evaluate this integral, you would just have to multiply this stuff out, right? You just do x minus 3 squared, multiply it with negative x, add 4x in, and then it would just be a polynomial, so it really wouldn't be that hard to evaluate. So I want to compare this now with what happened when we used the washer method, because I think a lot of students find the shell method a little confusing, just because it is a little harder to visualize. But in many cases, it's a lot easier than the washer method to set up. So let's remind ourselves what happened when we used the washer method. So when we use the washer method, we had to integrate with respect to y, first of all, right? Because the washers had their thickness in the vertical direction. And then because we had to integrate with respect to y, that meant that we had to take our function and solve it for x, which it took some steps to solve that for x. And then we actually had to separate our single function into two functions, right? One of those functions was the inner radius, one of them was the outer radius. It was a little tricky to figure out which one was which, but we figured it out. And then this is what we ended up with for our integral. So if you actually had to integrate this is a lot more complicated to integrate than what we came up with here as our answer, right? This one's just going to be a polynomial. That one involves square roots, so it's just going to be more complicated to evaluate. So even though the shell method may be a little harder to visualize, in this case, it is just so much easier to set up. All we really had to do is identify that the radius was x, the height was our function. We didn't have to solve anything, calculate anything. It was really straightforward compared to the washer method. So, just be aware, and this is something we'll talk more about in a later video about kind of how to decide which method to use. Be aware that even though the shell method might seem a little trickier, in a lot of cases it is actually easier.